All right. Hello, everybody. It's me, your Professor Sharif. I'm trying a trial run for one of our online meetings. Our online lectures now. Hopefully you can see me fine. I've got one other participant in here who may or may not show up. And let's just see if we can get started. So I'm going to go ahead and assume we're going to start Chapter 19 on enzymes. Give me 1 second to get everything ready here. And okay, I hope you can see this. So, Chapter 19, enzymes. So, enzymes are basically a type of protein. They're a particular kind of protein, and they specialize in catalyzing chemical reactions. They're not designed for structure or integrity. They are just designed to take one compound and convert it into a different type of compound. These reactions might happen normally without enzymes, but they happen very, very slowly. So they might take hours, days, or weeks for a particular reaction to take place without the aid of enzymes. With enzymes, they happen within seconds, almost instantaneously. So how do you classify an enzyme? Well, they're basically classified by what type of reactions they actually catalyze. So we have oxidoreductases, which are types of enzymes that oxidize and reduce their substrates. Transferases are enzymes which transfer some functional group or some part of a compound from one thing to a different thing. There are hydrolases, which are enzymes that catalyze hydrolysis reactions. So those are reactions that cleave bonds through the addition of water. Usually they're like polymer kind of compounds. So you can have hydrolases working on proteins to break up the amide bonds into individual amino acids. You can have hydrolases that hydrolyze glycosidic bonds and sugars, so on and so forth. Lyases are types of enzymes which catalyze either addition of compounds to double bonds or enzymes that produce double bonds. Lyases basically are enzymes that work on double bonds somehow. Isomerases are enzymes that specialize in isomerizing compounds, so they don't change the formula, they just change the arrangement of the atoms. And then ligases are particular enzymes that are usually involved in making complex macroscopic molecules, and they usually are energy dependent. I will get back to this figure in a bit. So enzyme classification. Oxidoreductases, like I said, are enzymes that catalyze oxidation reduction reactions. They have to do both, but they don't have to do both at the same time or on the same substrate. So an example of this might be lactate dehydrogenase, is an enzyme that oxidizes lactate and reduces NAD+. That's its cofactor. So here is the chemical schematic for that reaction. If you can see that, I've got lactate on the left, NAD+, lactate dehydrogenase is catalyzing the interconversion of those four compounds with each other. And so lactate is being converted into, that is pyruvate and NADH. Notice it's a double-headed arrow. A lot of enzymes, if they're not energy dependent, are reversible. Enzyme classifications are transferases. Like I said, those are enzymes that specialize in the transfer of one functional group or one part of a compound into a different compound. They might be subcategorized by what functional group they're transferring. So a transaminase is an enzyme that's a transferase, but it's transferring an amine, so it's a transaminase. You've got transmethylases, which transfer methyl groups. Kinases are a particular type of transferase, and these are actually pretty important biologically speaking. They get their own name, kinases, and those transfer phosphoryl groups through ATP. So here is a typical example of this hexokinase. I've got glucose on the left and a molecule of ATP. Hexokinase is taking that ATP, it's plucking off one of those phosphate groups and sticking it onto the 6th position of glucose over here. And ADP is the product of that. It's the remainder of the ATP compound. Hydrolases, like I said, catalyze hydrolysis reactions. Water is going to be incorporated into the product in some sense, but if this is in a body, there's going to be water all around, so that's not usually a concern for the enzyme. Here I've got an example of a lipase or a lipase, where I've got a triglyceride, a very, very short triglyceride over there on the left, 3 molecules of water, and the lipase is catalyzing the hydrolysis of that reaction into glycerol and 3 fatty acids. Animation's messed up on this slide, but I've got lyases, which I told you are involved in the enzymes that add and produce and react with double bonds. So they can either form double bonds or they can remove double bonds. They can do, if they're removing double bonds, it's an addition reaction. If they're producing double bonds, it's an elimination reaction. And if it's water, they are hydration and dehydration reactions, respectively. So in this example, I've got fumarate, which is reacting with fumarate over there on the left of the double bond. It's adding water across that double bond to give you the alcohol compound. I believe that's malate on the right. This is an enzyme that's involved in energy metabolism, the citric acid cycle, Krebs cycle, which we'll talk about if we get time this semester. Isomerases, like I said, just isomerize compounds. They don't change the formula. They just rearrange the atoms in that compound. So they're usually pretty similar in structure. Here I've got phosphoglycerate. Phosphoglycerate mutase is taking 3 phosphoglycerate. Glycerate is the carboxylic acid part, and this mutase enzyme is mutase is another synonym for isomerase. It's moving that phosphate group from the blue oxygen onto the green oxygen. Ligases, like I said, those are the ones that are involved in producing kind of more complex macroscopic molecules. So formal definition is they catalyze the formation and breaking of carbon-carbon bonds, carbon-oxygen bonds, and carbon-nitrogen bonds. A lot of things fall into that general category, so it's kind of loosey-goosey with this definition a little bit. But in general, 2 large molecules come together, and usually this requires energy input to produce 1 larger molecule, or a couple more complicated molecules. In this example, great example of a ligase is DNA ligase. You've got 2 strands of DNA that need to be stuck together. So I've got the tail end of one DNA over here and the head end of another DNA molecule over here. DNA ligase is going to use ATP to try to fuse this phosphate group onto this alcohol over here and produce 1 continuous long DNA strand. We've taken 2 complex molecules and we've combined them into 1 big molecule with the addition of energy. Their nomenclature, they're usually named after the substrate that they work on. So even without being familiar with the enzyme, you can probably do a decent job of guessing what that enzyme does. They all have the ACE ending, if you might have noticed. All the enzymes that are listed have the ACE ending. That is not the case for proteins, so that is a good way to distinguish enzymes from proteins. Lactase is an enzyme that catalyzes the hydrolysis of lactose. So you can see lactase, lactose. Say urease catalyzes the hydrolysis of urea. And then you also have particular enzyme names that refer to common reactions on many substrates. So dehydrogenase enzymes are enzymes that remove hydrogen. So these are lyases. They'd be producing double bonds usually, and they're dehydrogenating the compound. So they are dehydrogenases. Decarboxylases similarly remove carboxyl group CO2. Oh wait, that's carbon dioxide, and that's what these do. They take carboxylic acids and convert them into carbon dioxide and cut off a carbon and reduce the rest of the compound. It's kind of like cutting your oxidative losses. All right. There are systematic names for enzymes. They get a little bit more complicated. They involve the substrate of the enzyme, the type of the reaction that is catalyzed, and also any cofactors that are involved in there. So we talked about lactate oxidoreductase earlier, or maybe I think it was lactate dehydrogenase earlier. The systematic name for that compound, for that enzyme, would be lactate NAD oxidoreductase. It tells you this enzyme is working on two substrates, lactate and NAD. NAD would kind of be the cofactor or the coenzyme, and then oxidoreductase tells you that it's an oxidation reduction reaction. Activation energy. So enzymes are catalysts, and what is a catalyst, right? We usually think of a catalyst as like, oh, catalyst like makes a reaction go. Catalyst is a very particular definition. A catalyst is any substance which increases the rate of a reaction and is not destroyed or consumed in the course of the reaction. So, in theory, you can add one molecule of a catalyst to a reaction. I've got a bottle of some alcohol over here, and I add a little drop of one catalyst that converts that alcohol into acetic acid vinegar. There's catalyst makes that reaction happen much faster, and I only need one molecule of it to get it to go, even though it's a whole bottle of something. That turns out. We'll talk more about that later. How do catalysts do this? What they do is they lower something called the activation energy for a reaction. It's going to get a little bit thermodynamic-y, but if you pay attention, it's really interesting. So this is a general. This is comparing catalyzed and uncatalyzed reactions. So I've got a general reaction of A plus B goes to make C plus D. On the left figure, I've got let's see. So on the y-axis, I've got relative energies of the substrates. The higher the energy of the substrate is, that means it's less stable. And it will usually want to react in order to find itself in a lower, more stable structural level formation. So I've got reactants A and B are at higher energy than reactants C and D. That tells you that this is actually a favorable reaction. Those compounds are going to want to go down. But there's that you see that blue line, that curve, they got to go up before they can come down. That's the activation energy. They need to be raised up in their energy. They need to be heated or strained in some way that they are uncomfortable up there, but now they have a route down to the more stable C and D products. You can see in the uncatalyzed reaction that activation energy looks pretty substantial. It looks like it is at least twice, maybe 3 times the difference in energy of the reactants and the products in the first place. If you look on the right for the catalyzed reaction, we still have the same basic trend. And notice that the reactants and the products are still at the exact same energy states. That does not change. That is a state function and is independent of the enzyme. That never changes. That is a thermodynamic property of both those compounds. But the activation energy required to get from one to the other, that decreases significantly. It decreases to the point where it can occur under pretty mild room temperature body temperature conditions. Otherwise, that reaction just wouldn't take place. It doesn't have enough energy to make it go. Or you would have to heat up your sample to like 200 degrees in order to get it to go. That's not good for the organism. So if we can lower it down to 98 degrees, that's great. Okay, so substrates, just nomenclature. So substrates are converted into products. That's the typical nomenclature for describing an enzyme reaction. The energy difference between the substrates and the products is unchanged. Like I was saying, that difference in the energy of the compounds the enzyme is working on, that is not dependent on the enzyme at all. The catalyst changes the pathway, changes the route that compounds up here reach compounds down here. And instead of having to drive all the way up that hill to come down, they can kind of take a little side hill that might be a little bit lower energy. So in a general reaction, this has to do with equilibrium constants. So I have little a is your coefficient. So I've got, say, 1a going to make 1b, and then little a and little b will both be 1. The equilibrium constant, that's the KEQ, is given by the concentration of products over the concentration of reactants, and each of those would be raised to however many products or however many reactants are going in there. For most of these cases, it's going to be 1 and 1, most of them. So KEQ is an equilibrium constant, and it just measures the relative stabilities of those products, and that should be, like I said before, enzyme independent as a function of just the compounds. It defines the ideal final ratio of those reactants and products. It's a thermodynamic property, and KEQ does not have any effect on the kinetics of a reaction. Kinetics, I mean the rate, how quickly a reaction is. Basically, you have thermodynamics and you have kinetics. Thermodynamics tells you, well, if you wait long enough, eventually something will decompose into something else. I don't know how long it's going to take. It might take the whole universe's timeline, or it might happen in a couple seconds. But eventually it should happen. Diamond is energetically higher than graphite. So given a long enough time scale, all diamonds should eventually convert into graphite. But the kinetics don't permit that to happen on our time scale. It'll take a long time. Okay. Enzymes don't alter that chemical equilibrium for those reactions. If it was unfavored without the enzyme, it's still unfavored with the enzyme. The enzyme just helps it reach equilibrium faster. So the reaction will always proceed towards the direction of lower energy. That's like the second law of thermodynamics. Says that energy, I'm not going to get into it. For a reaction to proceed, it does need to overcome that activation energy. Enzymes, which are acting as catalysts, and catalysts in general do this particular thing. They overcome the activation energy. They actually lower the activation energy and effectively speed up the reaction. They don't force it to go. They just make it happen easier. They're like, never mind. Moving on, we've got substrate concentration and enzyme catalysts. So uncatalyzed reaction rates. If we look at the graphs on this slide, I've got an uncatalyzed reaction on the left, and on the y-axis I have the rate of the reaction, how quickly the reaction is going, and on the x-axis I have the concentration of reaction. We don't have a high concentration of things. Whatever reaction does happen is going to happen slow because those compounds have to find each other, right? So, but if you increase the concentration, the rate speeds up because they're hitting each other more and more often, coming into more and more contact. So the rate increases. If you look at an enzyme catalyzed reaction on the right, it starts off the same way. Low concentration, low reaction rate, and increases pretty dramatically, kind of linearly. And then if you look at it, it starts to curve off and actually level off. And it reaches a maximum rate, what they call the Vmax. This is the fastest the enzyme is able of doing this reaction. It's basically a measure of the turnover rate for each enzyme. The enzyme has to grab the substrate, do its reaction, let go of the product, and then start over. How long does that take? That becomes your rate limiting step. That is defined as the Vmax, the maximum rate. If you add more enzyme, Vmax will increase. If you add less enzyme, the Vmax will decrease. But the Vmax is a function of the enzyme. So the enzyme rate is initially responsive to substrate concentration. Like I said, it starts to go up, and then it kind of curves off and levels off once the enzyme becomes saturated with substrate. At that max point, if you froze time and looked at all the enzymes, all of those enzymes would be working as hard as they can. They can't work any harder. They can't do more than one thing at a time. So it's saturated. Okay. So how do enzymes actually do reactions? This is kind of the interesting part. Enzyme reactions usually occur in at least 2 stages. You could argue, I'm kind of being a little bit iffy here. So the first is the enzyme has to bind to whatever substrate it's working with. There has to be an enzyme substrate complex. They have to find each other and reach the right spots. Second step is actually conversion of that substrate into the product. So the substrate reacts, turns into the product, and then it's released from the enzyme. That second step is usually the slowest step. It's usually the slower step, and ends up limiting and defining the rate that enzyme can do its given reaction. It's called the rate limiting step. It's the slowest step in any reaction, and it ultimately defines how quickly everything gets done. It's kind of like if you have a line of people waiting at the store to check out, and you've got one person who's really slow. That person is the rate limiting step for you checking out. Okay, so as you can see, here's a more detailed description of the different states of an enzyme reaction, and it has more than 2 steps, but those 2 steps are included in this feature. Step 1 is the same as before, the formation of an enzyme substrate complex. So enzyme is E, substrate is S. Step 1, they bind to each other and form ES, the enzyme substrate complex. The substrate is going to bind to a particular spot in each enzyme called the active site. It's usually like a pocket or a cleft or a hole in the enzyme. It allows the molecule to kind of reach in and get right where it needs to be for the enzyme to kind of work on it. They're very specific in their reactions, so they have very specific active sites that will only accept certain types of substrates. They're very specific, usually. And these are also weak non-covalent interactions. The compound could just as easily go back, come into the enzyme, it can also leave without doing the reaction that happens. Okay, so in 1984, Emil Fischer proposes the lock and key model for how enzymes work. Because people were noticing, well, these enzymes are doing pretty particular reactions, but only on some substrates. So how is this? Why is it reacting with this substrate, but not this substrate? So the analogy that was developed, the model that was developed, was that each substrate fits into an enzyme analogously to how a lock fits into a key. You have to have the right key to fit into your lock, and then you can open your lock and get into your door. So here I've got these keys and locks and enzymes and substrates. I've got an enzyme. You can see it's got a little keyhole kind of carved into it, and you've got a good substrate which fits really well into that keyhole, and you get a bad substrate that is not going to fit into the keyhole. So this is kind of explains the specificity of some of these enzymes. Here's kind of another similar model where you can see the enzyme and the substrate kind of particular amorphous shapes. These are kind of simplified so that they're easy to look at. You don't actually have to look at functional groups and atoms and stuff, but the general conceptual point is the same. There are 2 lobes here for the substrate. There's a green lobe here and a green pointy lobe here, and there's a blue cleft here, and there's a blue pocket over here, and they fit into the enzyme substrate complex. That model worked pretty well, but it didn't really explain how the reaction takes place. So that model was eventually refined into the induced fit model in 1958. So in the induced fit model, when the substrate and the enzyme complex with each other, the enzyme and the substrate are not rigid. They're kind of flexible. And when the substrate binds, the enzyme kind of changes its shape a little bit to accommodate the substrate, and the substrate might accommodate its shape a little bit to fit the enzyme. That's part of the more of the reaction part. Initially, the enzyme might try to conform itself to fit a particular substrate. So there's a conformational change in the enzyme binding that primes it for the next step. So the ability to recognize and bind specifically to only one or a few substrates is kind of given by that. So here's a good example like I was describing earlier. If you take urea, which is there on the left, give it water and urease, it hydrolyzes urea into carbon dioxide and ammonia. No problem. Now, look at the next compound, methyl urea. Same thing as urea, they're just a little, we've taken one of the hydrogens, turned it into a methyl. Not that big of a change, but this enzyme doesn't work anymore. Can't do anything. It's stuck, doesn't know how to do. It's specific enough to tell that small change, just a little methyl group. Not all enzymes are this specific. Some enzymes are what they call them promiscuous enzymes. They just react with anything they can find. And there are most enzymes though are very specific. Okay, so 4 classes of enzyme specificity. You have absolute specificity. This is a loyal, faithful enzyme that has only one particular substrate. So the example here is amino acyl tRNA synthetase. tRNA is involved in translating DNA into protein. So it needs to be very faithful, it needs to have high fidelity to make sure your proteins are actually what they're supposed to be. Group specificity. This is where an enzyme is specific only to a particular group or part of a molecule or something. So hexokinases, they react with hexoses, sugars. They're pretty promiscuous with sugars, but they are limited to sugars. There are linkage specificity enzymes. These are like the hydrolases usually. These are enzymes that target a particular type of bonds that they're probably going to break in these forms. So protease is like a digestive protein or digestive enzyme that works on proteins. It tries to break up proteins into smaller bits. They're specific to the peptide bonds in each of the linkages of the protein. And then you have stereochemical specificity. This is where an enzyme is specific to a particular enantiomer. It's able to distinguish the D and the L in enantiomers or diastereomers of various sugars and amino acids. Okay, so we did step 1. Let's look at steps 2, 3, and 4. So in step in step 2, you can see it's making ES star. It's called a transition state. This is the high point in that activation energy. It's represented by that maximum point. And it's the least stable conformation. The transition state only exists for a second, and it's kind of like the in-between state of a reaction. We had to break one bond, but we haven't formed the next bond yet. Eventually, that produces the enzyme product complex, and the product and the enzyme can dissociate. So after binding, the enzyme and the substrate change their conformation to favor that transition state. That transition state is a result of that induced fit taking place with the enzyme. It's the intermediate state between substrates and reaction. It is very high energy state. It's the least stable in this whole chain, and it exists transiently. If it's down to the argument of does it exist if it only is around for 1 to the negative 20th seconds? Okay, so here's kind of my little figure here. I've got a reaction of B is going to form a bond with these things that kick off A. The transition state is, half of the bond with B is formed and half of the bond with A is broken. It's kind of weird. So it's the midpoint of a reaction, represents the least stable of those interactions. They exist very transiently, usually negative 30 seconds. Okay, it's a really small amount of time. What is the transition state, though, in the enzyme? So the enzyme is going to stress a bond, and that might promote bond breaking. The enzyme might also squeeze two substrates together if it's trying to promote a reaction between them. And the enzyme active site, where it's this particular spot on the enzyme, it might have particular amino acids right around there that are designed to change the microenvironment, so that although this whole solution is neutral, once it finds its way into that enzyme, all of a sudden it's pretty acidic. That might affect the rate of reaction. So I've got enzyme substrate complex, the transition state. You can see the green substrate is getting flexed a little bit, and then the enzyme product complex. We have broken the bond between the pentamer and the hexamer of the substrate, hexagon and pentagon of the substrates, and then each of those substrates can be released from the enzyme product complex. Here is an example of a bond-forming reaction, where we're going to start over here on the left. We've got two individual groups. We've got a hexose and a pentose over here. I'm guessing because those are supposed to be oxygens. So they bind to get to the transitions. They bind to form the enzyme substrate complex. Then there's a transition state which forms the bond formation to give me the step 3 enzyme product complex. The transition state should really be in between here. They probably should not have said transition state at 2. It should have been right in this point between 2 and 3. And then enzyme product complex can be ejected from the enzyme to give you the enzyme and the product separately. and then the enzyme can repeat that cycle over and over again. In this example, it looks like it's forming a glycosidic bond between glucose and fructose. Those are the hexoses and the lactoses. Cofactors and coenzymes. So many enzymes need prosthetic groups. We talked about those before with proteins. So heme was like the prosthetic group for hemoglobin, which transport oxygen. So enzymes might need those prosthetic groups or those cofactors in order to actually carry out the reaction. Without those cofactors, they can't do it. It's like asking a surgeon to do something without a scalpel. So here I've got so the protein component of this, just the enzyme without any complex or cofactor is called the apo enzyme. The non-protein component is called the prosthetic group or the cofactor or the coenzyme. All those terms are kind of used synonymously with one another. It's non-peptidic. They're usually vitamins, actually, in these cases. A lot of times they just end up being vitamins that you take with your breakfast or whatever. And finally, once in this figure, you can see once the coenzyme and the apoenzyme have formed, they've formed the holoenzyme or holoenzyme. That is a functioning enzyme complex. That one can react with substrates and start doing reactions. So those cofactors, like I said before, so they can be metal ions too, like iron in the case of heme and hemoglobin. That's not really an enzyme. And they can also be organic compounds, and usually they are vitamins. So here I've got my apoenzyme and my substrate. They can't do anything. There's no reaction right here. If I add copper to it, that's going to be part of my cofactor right here, or coenzyme. Now I've got an active holoenzyme. That holoenzyme can react with the substrate and do whatever reaction needs to get done. So coenzymes are organic molecules that serve as the carriers for electrons or those chemical groups. Can be acceptors or donors of either. Vitamins are really common, like I said. Of the water-soluble vitamins, all but vitamin C work as coenzymes. And a vitamin is comes from the terminology of vital amine, because the first vitamins were amines, they're not all amines. You need them to live. Your enzymes actually need them to be themselves. All right, I think I'm going to stop there for now, and hopefully this is going well. So thanks for watching, everybody. How do I do this? How do I stop?